Welcome to this video on electrical earthing for HT and LT systems. We will cover design principles, standards including IS 3043, IEEE 80, NEC, calculations, and inspection procedures. Our video is structured into 8 modules, starting with the fundamentals and governing standards of earthing. We will then explore different earthing system types, detailed design requirements for HT and LT systems, and the selection of earth electrode types. Earthing, or grounding, electrically connects metallic parts to the earth for safety and system stability. Its purpose is to protect personnel from shock, limit overvoltages, and ensure protective devices operate reliably. It applies to both HT systems over 1 kV and LT systems 1 kV and below. We review 4 main earthing systems per IEC 60364. TNS offers maximum safety with separate neutral and earth conductors. TNC combines them, but new installations are restricted. TNCS is common in the UK and Europe. TT uses separate earth electrodes, requiring residual current devices for protection. IT systems are isolated for continuity in critical operations. HT earthing design focuses on robust earth grids. Key requirements include an earth resistance of 1 ohm or less for substations, use of plate or pipe electrodes, and meeting step and touch potential limits per IEEE 80. Separate earth pits are mandatory for equipment, neutral, and lightning protection. HT electrode specifications detail acceptable materials and sizes for plates, pipes, rods, and strips, typically buried at least 0.6 meters deep. Conductor sizing must withstand fault current. Step and touch potential limits are calculated per IS 3043 and IEEE 80. Testing requires a fall of potential test, aiming for below 1 ohm, and repeating tests every 2 years or after major work. LT earthing designs target a maximum resistance of 5 ohms. Requirements include a minimum of 2 independent earth pits per substation and mandatory use of 30 milliamperes residual current devices for socket circuits. Equipotential bonding is crucial, connecting all metal pipes and structures. PE conductors must be green and yellow sleeved. Electrode selection criteria are based on soil resistivity and application. Options include pipe, plate, rod, strip, mesh/grid, and foundation earth, each with specific dimensions and typical resistance ranges. Soil resistivity testing using the Wenner 4-pin method is vital before finalizing the design. Soil resistivity varies significantly, from under 1 ohm meter in wet ground to over 5,000 in gravel. Formulas for calculating resistance in pipe and plate electrodes and conductor sizing are based on international standards. HV substations typically require less than 1 ohm, while LT installations aim for less than 5 ohms. For power transformers, neutral earthing is solid for HV windings, and tank and core earthing must be separate. HT switchgear earthing ensures all panel frames and bus trunking are bonded. Cable earthing practice depends on core type. Lightning protection requires dedicated earth pits. Neutral earthing methods vary, using solid, NGR, or zigzag transformers. Our compliance checklist covers the design phase, material and installation, and testing and verification. Key items include soil resistivity surveys, defining resistance targets, ensuring correct conductor sizing, proper backfill material, and mandatory annual inspection and testing to maintain safety compliance. In summary, earthing is mandatory for safety, governed by key international standards. HT systems require robust design and low resistance, while LT systems mandate RCDs and equipotential bonding. Selection must be based on soil resistivity, and conductor sizing must withstand fault current. Annual testing is non-negotiable. A well-designed earthing system protects life, equipment, and continuity.